Good day, MT1. Welcome to our discussion for the first part of Module 8, which is about carboxylic acids and esters. This topic or this module is your final module for MTChem 1 lecture. I am your module writer, Ms. Angela Joy Lozano. Let's start with looking at our outline or overview for the first part of Module 8. These are the topics and subtopics to be discussed for this module. First, for carboxylic acids, we will be discussing the structures and the derivatives, followed by the discussion about the nomenclature or the naming of the compounds. We'll also be tackling about the polyfunctional carboxylic acids and then proceed with the discussion of the acidity of carboxylic acids. After that, we'll start with the structures and examples of esters, the process of esterification, and of course the nomenclature or the naming of ester compounds. For the last part of our Module 8, Part 1, we will be discussing about the physical properties and reactions of both carboxylic acids and esters. For carboxylic acids, we will be talking about the carboxylic acid salts and its uses, and for esters, we will be delving further about the process and reaction of ester hydrolysis and saponification. Let's take a look at our objectives for Module 8. Our general objective is to determine the physical and chemical properties of carboxylic acids and their derivatives, along with amines and amides, and their classical and IUPAC nomenclature. For the first part of Module 8, our objectives at the end of this lecture is that you should be able to determine the correct way of naming carboxylic acids and esters, be familiarized with the structures of carboxylic acids and esters, and identify the chemical reactions which involve carboxylic acids and esters. Let's start with the first part of our Module 8, which is carboxylic acid. Let's take a look at the outline again. For carboxylic acids, we will be discussing first the structure and derivatives, the naming and nomenclature of carboxylic acids, specifically the IUPAC and common names. We'll also be discussing about the polyfunctional carboxylic acids, which are divided into 3 subtopics, and of course, the acidity of carboxylic acids. Let's start with the structure and derivatives. Now, carboxylic acid is an organic compound whose functional group is a carboxyl functional group. If you remember in the past module, you've talked about the 2 families of compounds, which are aldehydes and ketones. The functional group of aldehydes and ketones are a carbonyl group. Carboxylic acid, on the other hand, has a carboxyl functional group. But what is a carboxyl group? It is a carbonyl group, which is carbon double bonded to O or oxygen with a hydroxyl group bonded to the carbonyl atom. So what is its appearance? It looks like this. Okay? Again, if you were to go back to our past module, you might remember that the carbonyl group, which is C double bonded O, this is our carbonyl group. Carboxyl, on the other hand, is a combination of both the carboxyl and the hydroxyl group. So we have here our carbonyl, and we have here our hydroxyl group. Okay, so carboxyl is a combination of carbonyl and hydroxyl group. That is the difference with aldehydes and ketones. So the general structural representation of a carboxyl group is a carbon double bonded to O, which is our carbonyl, and then that carbon is also bonded to our hydroxyl group, and then we have our R or rest of the group attached to our central carbon. There are also abbreviated linear designations for the carboxyl group, and these are COOH or CO2 For uniformity, we'll be using COOH in our discussion. And then upon seeing this COOH, okay, this refers to carboxylic acids. Kindly remember that. Again, an organic compound whose functional group is the carboxyl functional group is what we call the carboxylic acids. Even though it is a combination of both the carbonyl group and the hydroxyl group, the carboxyl functional group has a set of unique characteristics different from its component parts. Okay? It does not show characteristic behavior that is either in the alcohol, which is the hydroxyl group, or the aldehyde and ketones. Okay, it has a completely different set of characteristics. Let's proceed now with the simplest carboxylic acid that we can find in our environment. First, the simplest carboxylic acid, of course, is it has a hydrogen atom attached to the carboxyl functional group. So we have here our carbonyl, we have our hydroxyl, and then we have our hydrogen attached to our central carbon. This is our simplest carboxyl acid. Next, structures for the next two simplest carboxylic acids are those with methyl and ethyl alkyl groups. Okay, we have here our methyl group, and then we have our ethyl alkyl group, and then we have here our carboxyl functional group. Now, how about for the simplest aromatic carboxylic acid? Kindly remember that cyclic carboxylic acids do not exist. Let's take a look at first our simplest aromatic carboxylic acid. As you can see, we have here our benzene ring, and in here attached is a carboxyl group, our carboxyl group. Why do cyclic carboxylic acids do not exist? Okay, this is similar to the non-existence of cyclic aldehydes. Remember that carbon can only form 4 bonds. Okay, so meaning this carbon right here already has 4 bonds. It has 1 bond bonded to the OH or the hydroxyl group, 2 bonds bonded to our oxygen, and 1 bond bonded to the carbon in our benzene ring. A cyclic carboxylic acid means that the carbon should have 5 bonds because, as you can see, it is bonded 1 in here, bonded another in here, so those are already 2 bonds. And then for the carboxyl group, it should be bonded twice for the oxygen and once for the hydroxyl. So these are 1, 2, 3, 4, 5 bonds, and this is not possible. That's why cyclic carboxylic acids do not exist. Okay? So we only have this simplest aromatic carboxylic acid. Hopefully, you're already familiar with the functional group of our carboxylic acid. Again, it is simply a combination of our carbonyl, which is C double bonded to O, and a hydroxyl, which is bonded to our carbonyl carbon atom. Okay, so this is our COOH, or our carboxyl functional group for carboxylic acids. Let us now proceed with the carboxylic acids derivatives. Carboxylic acid derivatives are organic compounds that can be synthesized from or be converted into a carboxylic acid. This means that there are different chemical reactions that can happen in carboxylic acids that can produce these derivatives. And these derivatives can be converted back into a carboxylic acid. The group attached to the carbonyl atom distinguishes the derivatives from the others. Later on, you'll be understanding or we'll be explaining further what this means. But for now, let's take a look at the 4 carboxylic acid derivatives, which are esters, amides, acid anhydrides, and acid chlorides. At the last part of our discussion for the part 1 of Module 8, we'll be discussing much further about esters. And then in the second part of Module 8, we'll be discussing more about amides. Now, here are the structural representation of the different carboxylic acids. Again, as mentioned a while ago, the group attached to the carbonyl carbon atom distinguishes the derivative types from the others and from carboxylic acid. So that we can compare these derivatives from the carboxylic acid functional group itself, let's write the carboxyl functional group, which is carbon double bonded to O for the carbonyl, and then we have a hydroxyl attached to our carbonyl carbon atom. Then we have here the rest of the molecule. Okay, so this is our carboxylic acids. Now for the first one, this is ester, amides, acid anhydrides, and acid chlorides. Mentioned a while ago that the group attached to the carbonyl atom is what distinguishes them from the others. So we have here our carbonyl atom. Okay, so in our ester, okay, the group attached to it is an OR group. For amides, the group attached to it is an NH2 group. The acid anhydride is an OOR. And then acid chloride is simply chloride attached to it. Okay, so this is what distinguishes them from the other. Okay, as you can see, there are different groups attached to our carbonyl carbon atom. Okay, and this is what differentiates them from each other. Okay, hopefully you understand the differences between the different carboxylic acid derivatives. Let us now proceed with the IUPAC nomenclature and the common names of carboxylic acids. Let's start first with the IUPAC nomenclature of carboxylic acid, starting with monocarboxylic acid. As mentioned during the discussion of our outline, naming is divided into three parts, which is monocarboxylic, dicarboxylic, and aromatic carboxylic acids. Let's take a look at the rules for naming the monocarboxylic acids. First, what are monocarboxylic acids? From the name itself, it only has one carboxyl group present on the whole compound. So here are the steps. First, you need to locate the carbon atom of the carboxyl group as the parent chain. And then you need to select the longest carbon chain that includes that carbon atom of the carboxyl group as the parent chain. Next, name the parent chain by changing the E ending of the corresponding alkane to oic acid. Next step is to number the parent chain by assigning the number 1 to the carboxyl carbon atom. And last, you need to determine the identity and location of any substituents, if there are any, in the usual manner, and append this information to the front of the parent chain name. Here are the rules. Okay, just by looking at them, they might seem vague, they might seem confusing. So let's discuss the steps one by one. We have here an example of a monocarboxylic acid. Let's try to name it by following our steps. So first, we have to locate the carbon atom of our carboxyl group. And then we have to consider that as part of our parent chain. So we have first locate the carboxyl group. So here is our carboxyl group. Okay, we have here our carbon. So let's just put the carbons in here. Okay, so we have our carbon double bonded to O. This is our carbonyl group. And then our OH, which is the hydroxyl group. We're now done with our first step. Okay, that's easy. Next, For the next step, select the longest carbon chain that includes the carbon atom of the carboxyl group as the parent chain. For this one, it's not that hard to look for the longest chain since our compound is a linear compound. All we need to remember is that you always need to include the carbon atom in that longest chain. So we have here 1, 2, 3, 4, 5. This compound has 5 carbons. Okay. Let's proceed with our next step. For the next step, name the parent chain by changing the E ending to the corresponding alkane to oic acid. First, let's try to name this alkane. Okay, this alkane, since it has 5 carbons, this is now pentane. But it says here to name the parent chain by changing or dropping the E. Okay, we need to drop the E and change it to oic acid. So our name now for this compound will be pentanoic acid. Okay, so this compound is now pentanoic acid. Next, number the parent chain by assigning number 1 to the carboxyl atom. Since this one has no derivatives or has no substituents attached to it, and it's understandable that the carboxyl atom is number 1, we don't need to indicate or to put number 1 in this name. Okay, so it's still pentanoic acid. Next step is to determine the identity and location of any substituents in the usual manner. In our last compound, in the pentanoic acid, we don't have any substituents situated in there. So we have a new compound as an example. First, let's try to do our first step, which is look for our carboxyl group. So our carboxyl group is this one. And our carboxyl carbon atom is located here. Okay, so we have our double bond O and our hydroxyl group. Rule number 2. Okay. You have to look for the longest chain that includes our carboxyl carbon atom. So we have here 1, 2, 3, 4. Okay, and then we have another chain which is 1, 2, 3, 4, and 5, which means we'll be following this line. Okay, this will be our parent chain. So we have 5 carbons as our longest chain. So this will be again pentanoic acid. But we still have our substituents. Okay. For our substituents, what we need to do is determine the identity and location of any substituents. First, let's identify them. So we have here bromine, so which will be put in the name as bromo, and we have a methyl alkyl group, so it will be methane. And then determine their location. Bromo or bromine is located in carbon number 2, so it will be 2 bromo. And methyl is on number 3. Okay. Now we just need to append this information to the front of the parent chain name. So we need to put them in order. So we have 2 bromo, 3 methyl, pentanoic acid. Okay, let's check if it's correct. Okay. The final name for this compound is 2-bromo-3-methyl-pentanoic acid. That's easy. You just need to follow the rules in naming carboxylic acid or monocarboxylic acid. Let's try some exercises to practice naming monocarboxylic acid. For this exercise, I advise you to get a scratch paper for you to be able to solve and to name it on your own. You may pause this video so that you can have more time in naming them. For the first one, we have to locate our carboxyl group, which is located in here. And then this is our parent chain. We have to identify the longest parent chain that includes the carbon atom of the carboxyl group. So this should be included. So we have here 1, 2, 3, 4, or it can also be this one as 4. So since both of them have the same length, you can choose which is your parent chain. So we have 4 carbon chain lengths, which is butane. And then as stated in the rules a while ago, we will be dropping the last E and changing it to oic acid. So this will now be butanoic acid. Let's now proceed with naming the substituents. We have here a methyl alkyl group, which is located in carbon number 3. So what will be the final name of this compound? Final name will be 3-methylbutanoic acid. Hopefully you got this right and you also answered at the same time. Let's proceed with the next one. For exercise number 2, we have this compound. For the first step, we have to identify and locate the carbon of the carboxyl group, which is located here because this is our carboxyl group. Next is find the longest parent chain. So we have 1, 2, 3, 4, 5 carbon length, which is pentane. Change E to oic acid, so this is now pentanoic acid. Now we have a substituent which is a hydroxy. Okay, and it's located in 3, carbon number 3. So this is now 3-hydroxy. For the final name of this compound, we have to append this name of the substituent to our parent chain. So our final name will be 3-hydroxypentanoic acid. Hopefully you're following through. Let's have another example. For this one, again, locate the carbon of the carboxyl group, which is this one, and label it as number 1. And then locate the longest chain. This is also, again, a linear chain. So we have 1, 2, 3, 4 carbons. So this is a 4 carbon length chain, which is now butane. Dropping E, changing it with oic acid, it becomes butanoic acid. And then we have a substituent, which is bromo or bromine, located at our 3rd carbon. So it will be 3 to indicate the location. And then append this on the front of our parent chain. So our final name for this compound is 3-bromobutanoic acid. Okay, this is the last part of our exercise for monocarboxylic acids. Hopefully you followed through with our exercises and you understood the process and the rules in naming monocarboxylic acids. So we're done with an IUPAC nomenclature of monocarboxylic acids. Let's now proceed with the dicarboxylic acids. If monocarboxylic acids are carboxylic acids that has only one carboxyl group attached to them, dicarboxylic acids, on the other hand, has 2 carboxyl group present, one at each end of the carbon chain. So they are both at the end of the carbon chain. So how do we name this dicarboxylic acids? All you need to do is to append the suffix dioic acid to the corresponding alkane name. The last E of the alkane in this part is retained to facilitate pronunciation. Okay, so we don't need to remove the last E. Let's take a look at this one. First, locate the carbons. So we have 1, 2, 3, 4, 5. For this one, you don't need to name which is which, or which is number 1, which is number 5. Okay? They do not need to be specified because they will always be at the two ends of the chain. So we have here 5-carbon chain. This is pentane. Now, since as written here, E is retained and you just need to add the suffix dioic acid. So this will now be pentane dioic acid. That's simple. All you need to do is add the suffix dioic acid to your alkyl name or alkane name. Let's try this one. So in here we have another dicarboxylic acid. We have here 1, 2, 3, 4 carbon chain, which is butane. Okay? So this will now be butane dioic acid. Again, you simply need to add dioic acid at the end of our alkane name. Let us now proceed with our next exercise or next example. As you can see in this one, we have a substituent present in our compound. First, let's try to number and locate our carbons. So we have here 1, 2, 3, 4. Now, I know I said a while ago that you don't need to mind, okay, or you don't need to specify the location of the carboxyl atoms or the carboxyl carbon atoms. But for this one, we need to name or we need to number our carboxyl atom so that the substituent will be at the lowest number. Okay? If we try to number it like this, 1, 2, 3, 4, the location of the substituent will be at carbon 3. But if we try to start numbering by the other end of our chain, this is 1, 2, 3, 4, our substituent now is located at carbon 2. So instead of naming it carbon 3, or instead of locating it at number 3, we will put number 2. Okay? So the location of our hydroxyl group is at 2 hydroxy. And then we have 4 carbon. This is a 4 carbon chain length. This is butane. Again, in naming dicarboxylic acids, you just need to add dioic at the end of the alkane name. For the suffixes, you just need to follow our rules for monocarboxylic acid wherein you identify the location, you identify the kind of substituent it is, and then you just put it or append it at the front of our parent name. So the final name for this one is 2-hydroxybutane dioic acid. Okay, again, in naming the substituent, we have to choose the number that is the lowest. So this is 2-hydroxybutane dioic acid. Hopefully, you follow through with our example. So we're done with both monocarboxylic acid and dicarboxylic acids. Let's now proceed with aromatic carboxylic acid. We're still in the IUPAC nomenclature or IUPAC naming system. For aromatic carboxylic acids, we have to remember that the simplest aromatic acid is simply called benzoic acid. Okay? Combination of the benzene ring and the oic, the suffix oic acid. Okay, and this is the appearance. Other simple aromatic acids are named as derivatives of benzoic acid. Benzoic acid is always our parent name for aromatic carboxylic acids. Okay, and the others are just simply derivatives. In benzoic acids, the ring carbon atom bearing the carboxyl group is always number 1. So this is now our number 1. Again, ring carbon, the carbon atom containing the carboxyl group is always the number 1. Let's try to look at some examples and exercises. Okay. For this one, we have a substituent, which is a hydroxide. Okay? Again, in naming substituents, we have to choose the lowest number for the location. Please remember that always number 1 is the ring carbon atom bearing the carboxyl group. So this is number 1. And then we will put this number 2, 3, 4, 5, 6. So now our hydroxyl group is at number 2. So what will be the final name of this aromatic carboxylic acid? It will be named as 2-hydroxybenzoic acid. Again, you just need to append the name of the substituent to our parent name, which is the benzoic acid. The location, the name of the substituent, and then our parent name. That's how simple it is. Let's try to practice again. Another one. For this one, we have number 1, the ring carbon bearing the carboxyl group. 2, 3, 4, 5, and 6. Whether you go this way, it's still 1, 2, 3, 4, 5, 6. The location of the chloride is at carbon number 4. So this is now 4-fluorobenzoic acid. Location of the substituent, name of the substituent, and then your parent chain name. Hopefully you're following through. We're now done with the IUPAC nomenclature or the IUPAC names of monocarboxylic acids, dicarboxylic acids, and aromatic carboxylic acids. Let's now proceed with the common names. For the common names, we'll just be discussing the monocarboxylic acid and the common names for the dicarboxylic acid. Common names of carboxylic acids. Okay, the use of common name is more prevalent in carboxylic acids, unlike any other of the organic compounds. Okay, the reason for that is carboxylic acids are one of the earliest classes of organic compounds to be studied due to their abundance. Carboxylic acids can be found anywhere in nature and they can be easily studied. That's why they were the first ones to be classified. We are already studying them even before the establishment of the IUPAC naming system. That's why it's much more common to use the common names. Their common names are usually derived from some Latin or Greek words that is related to the source of the said acid. Let's start first with monocarboxylic acids. Again, this is formed by taking the Latin or Greek root of the name for the specific number of carbon atoms and then adding the suffix "ic" acid. Let's take a look at this table. This table shows us the length of the carbon chain up until 6, the IUPAC name, comparing it with the common name, where is it found, and what is the Latin or Greek root word, along with its meaning. For a single carboxylic monoacid, we have here the IUPAC name methanoic acid with the common name formic acid. Formic acid is found in the stinging sensation in red ant bites. So when an ant bites you and then you experience that stinging or that itchy sensation, that is the formic acid in action. Formic acid, the name is from the Latin word formica, which means ant. So we are getting our root name, which is form, and then adding the suffix ic acid. So it's formic acid. Next is C2 monoacid with the IUPAC name ethanoic acid. Common name is acetic acid. You're familiar with this. This is found in vinegar. And it's from the Latin root word acetum, which means sour. Okay, acetic acid is what gives vinegar its tangy, sour flavor. C3 monoacid or propanoic acid in IUPAC naming, with the common name propionic acid, found in the smallest acid in fat. This is from the Greek word protos, which means first, and pion, which means fat. Okay? This is the smallest acid in fat. C4 monoacid with the IUPAC name butanoic acid, with the common name butyric acid, found in rancid butter. Okay, this is from the Latin word butyrum, which means butter. Okay, as you can see, we get the root word, which is butyr, adding the IC acid or ic acid, which results to the common name butyric acid. Next is the C5 monoacid or the pentanoic acid with the common name valeric acid. This is usually found in valerian roots, which has the strong odor. This is from the Latin word valere, which is to be strong, signifying the strong odor of valerian roots. And then the last is C6 monoacid, which with the IUPAC name hexanoic acid and common name caproic acid. Caproic acid is responsible for the odor and skin secretion of goats. So this is found or this is responsible for the odor of goats. Caproic acid is from the Latin word caper, which means goat. Okay? So of course, monocarboxylic acids do not only end in C6. Here are some of the lists, okay, of the other carboxylic acids common name. Carbonic, formic, acetic, propionic, butyric, valeric, caproic, enanthic, caprylic, pelargonic, and capric acid. Okay, this is until C10 monoacid, meaning there are 10 carbons in the carbon chain. All you need to remember in here is that it is formed by taking the Latin or Greek root word of the name for the specific number of carbon and then adding the suffix "ic" acid. Now you might be asking, do you need to memorize these common names? Since again, as mentioned a while ago, common names of carboxylic acids are more prevalent than the use of the IUPAC name. So yes, you need to memorize these common names. We're done now with the common names of monocarboxylic acids. Let's proceed with the dicarboxylic acids. Let's take a look at the table of dicarboxylic acids, showing the length of the carbon chain, their IUPAC name, their common name, and where they are found. First, we have the C2 diacid, or with the IUPAC name ethane dioic acid, with the common name oxalic acids, which are found in the genus Oxalis plants. C3 diacid or propane dioic acid, with the common name malonic acid, which is found in the fermentation of glucose. C4 diacid or the butane dioic acid, with the common name succinic acid, and the pentane dioic acid with the common name glutaric acid. Both of these play important roles in biochemical reactions. C6 diacid or the hexane dioic acid, or with the common name adipic acid, can be found in beet juices. C7 diacid, on the other hand, or with the IUPAC name heptane dioic acid, sorry, that's a typo, and with the common name pimelic acid, is found in small planktons. We're now done with discussing the structure and derivatives of carboxylic acids, the IUPAC nomenclature, and their common names. Let's now proceed with looking at the different polyfunctional carboxylic acids. In the discussion of polyfunctional carboxylic acids, we will just be explaining them, okay, or defining them and giving some examples. Now, what are polyfunctional carboxylic acids? Carboxylic acids that contain one or more additional functional group aside from one or more carboxyl groups. Okay, so aside from having a carboxyl group, they also have another functional group. They may occur in fruits, involved in the human body functioning, or even in skincare products or prescription drugs that we use. So carboxylic acids are very rampant or very common in the materials or even in our body that we use. There are three types of polyfunctional carboxylic acid. We have the unsaturated acids, hydroxy acids, and the keto acids. From the name themselves, you might have an idea what these polyfunctional carboxylic acids are. Let's take a look at the first one, the unsaturated acids. Unsaturated monocarboxylic acids look like this one. And then as you can observe, we have a double bond. Okay, that is what makes it unsaturated. This is now what we call an acrylic acid, or if we are to name it in an IUPAC name, this is a propanoic acid. We have three carbons and a double bond, which makes it propene, and then adding the oic acid after dropping the E. So this is propanoic acid. Another example is an unsaturated dicarboxylic acid. We have here both butane dioic acid. Both of these are butane dioic acid. But what are their differences? Their difference is their isomers. Okay, this is a maleic acid. Next one is a fumaric acid. Okay, and then as you can observe, only the positions of their carbons are different, but this change in the position affects the function, right, of the acid. So even if these two are both butene dioic acid, they have different common names. This is maleic, this is fumaric. Another example of a polyfunctional carboxylic acid is a hydroxy acid. From the name itself, it has an OH functional group. For this one, we have the glycolic acid. I usually hear this in skincare products. So we have the common name 2-hydroxyethanoic acid. Okay? This is the OH group. Next one is the 2-hydroxypropanoic acid, or also known as a lactic acid. These are the common names. And then as you can see, you're much more familiar with the common names than their IUPAC names. Another type of a polyfunctional carboxylic acid are keto acids. It contains a carbonyl in the carbon chain itself. So we have here our carboxyl group. Of course, we have our carboxyl group. And then we have our carbonyl group for the keto acid. Okay, what is the name of this compound? This is now 2-oxopropanoic acid. Oxo stands for the keto or the keto functional group. And its common name is pyruvic acid. Hopefully you're familiar with the definitions of the different polyfunctional carboxylic acid. Let's now proceed with the discussion of the acidity of carboxylic acids. From the name itself, carboxylic acids, you can easily identify or you can easily refer that carboxylic acids are acidic, okay, but they are considered as weak acids. When placed in water, hydrogen ion transfer occurs to produce hydronium ion and carboxylate ion. So if you put this carboxylic acid or weak acid with water, okay, the H, okay, or the hydrogen ion transfers to the water to create a carboxylate ion. As you can see here, upon mixing it with water, the hydrogen bond between the OH group breaks, and then hydrogen transfers with water, and then we are left with a carboxylate ion. Again, This is the carboxylate ion, leaving us with a negative charge oxygen. Now, what is this carboxylate ion that we are talking about? Negative ion produced when a carboxylic acid loses one or more acidic hydrogen atoms. Again, when you mix carboxylic acid with water, since it's a weak acid, it loses its acidic hydrogen atom, leaving us with a carboxylate ion, which is a negative ion. Monocarboxylic acids always carry -1 charge. Dicarboxylic acids possess -2 charge. As you can see in this one, we have here the acetic acid combined with water. The hydrogen in the hydroxy group of the acetic acid is transferred into the water, which creates hydronium ion, leaving us with an acetate ion. Please remember that in naming carboxylate ions, we replace the ic acid of the parent acid with ate. So instead of having acetic acid, we remove ic acid and replace it with ate ion, which becomes acetate ion. Okay? We're now done with carboxylic acids. Again, let's have a quick overview of what we've already discussed. For carboxylic acids, we've discussed about the structures and derivatives, the IUPAC nomenclature and the common names of monocarboxylic acids, dicarboxylic acids, and aromatic acids. Polyfunctional carboxylic acids are also discussed and some examples. And we've also discussed about the acidity of carboxylic acids and how it produces carboxylate ions. For the next part of our module, kindly take a break before you proceed with the discussion of esters along with the physical properties and reactions of both carboxylic acids and esters.